You think you know what an atom looks like. Of course you do. You've seen the picture 1,000 times. A nucleus in the center, electrons circling around it like tiny planets orbiting a sun. Neat, clean, simple, easy to draw on a napkin. That picture is wrong. Not a little wrong. Not close enough. Not good enough for everyday purposes. Wrong. Fundamentally, completely, structurally wrong. Wrong in a way that should make you question every other thing you think you learned in science class. The atom is not a miniature solar system. It never was. And the moment you accept that, the moment you really let that in, everything you think you know about matter, about solidity, about the physical world starts to crack. So let me tell you what's actually inside an atom. And I'm warning you now, you're not going to like it. Because what's actually there is so strange, so deeply contrary to everything your brain expects, that your instinct will be to reject it. Don't listen, because this is what's real. Let's start with the simplest atom in the universe. Hydrogen. One proton, one electron. That's it. The simplest possible system. The atom everyone uses to teach physics, because it's supposed to be easy to understand. So, where is the electron? You want to say it's out there somewhere, circling the proton. Maybe on the left side right now. Maybe on the right side a moment later. Somewhere. A definite place. Because that's how objects work. Things are somewhere. They have positions. They occupy space. The electron doesn't have a position. Not because we can't measure it well enough. Not because our instruments aren't precise enough. Because the electron itself, the actual physical electron, does not have a definite location until the moment you measure it. This is not a philosophical debate. This is not a matter of interpretation. This is what the mathematics says. This is what every experiment designed to test this question has confirmed over and over for 100 years. Before you measure it, the electron exists in what we call a superposition. It's not here, it's not there, it's not secretly in one place, and we just don't know which. It genuinely, fundamentally has no location. What exists is a mathematical object called the wave function. The wave function tells you the probability of finding the electron in different places if you were to look. In some regions, the probability is high. In others, it's low. In some places, it's exactly zero. You will never find the electron there, ever. But here's the part that breaks something in your brain. The electron isn't hiding in one of those high probability spots before you look. It's not like a coin that's already heads or tails and you just haven't checked. It genuinely doesn't have a location. The wave function isn't a map of where the electron is. The wave function is the electron. That's all there is. Until you measure it. Stop. Think about what that means. An object, a physical object, without a location, until the act of observation creates one. Now let's talk about orbits, because this is where the solar system picture doesn't just bend, it shatters. You picture the electron looping around the nucleus in a smooth circular path, round and round, like a satellite around Earth. It feels intuitive. It feels right. It's wrong. Here's why. If an electron were actually orbiting like that, it would be accelerating, not speeding up necessarily, but changing direction constantly. And anything moving in a circle is accelerating, even at constant speed, because acceleration includes changes in direction, not just changes in speed. And here's the critical fact from electromagnetism. Accelerating charged particles radiate energy. They emit light. This is not theory. This is measured. This happens. It's basic physics. So if the electron were really orbiting the nucleus, it would be constantly radiating energy, losing it. And as it lost energy, the orbit would shrink. The electron would spiral inward, faster and faster, closer and closer to the nucleus, until it crashed into the proton. And the atom would collapse. How long would this take? Do the calculation. About 1/10 trillionth of a second. Every atom in the universe should collapse almost instantly. That obviously doesn't happen. Atoms are stable. They persist. They build chemistry, biology, you. So the electron cannot be orbiting. Period. Okay, you say, fine, no orbiting. Maybe the electron is just sitting there, stationary, held in place by the electric attraction between its negative charge and the proton's positive charge. Balanced, still, also wrong. If the electron were sitting perfectly still, we would know two things about it simultaneously. Its position, right there, its momentum, zero. And quantum mechanics says you cannot know both of those things at the same time. Not because of measurement limitations, not because of instrument imperfections, because nature itself does not allow it. This is Heisenberg's uncertainty principle. It is a fundamental structural feature of reality. Pin down position. Momentum becomes uncertain. Pin down momentum. Position becomes uncertain. You cannot have both, ever. So the electron is not orbiting, and it's not sitting still. So what is it doing? Nothing. It's not doing anything. It just is. It exists as a wave function, a mathematical description of probabilities. And that wave function has specific allowed shapes. We call these shapes orbitals. And here is where most people get confused, because the word orbital sounds like orbit. It isn't. An orbital is not a path. It is not a trajectory. The electron follows. It is a region of space, a shape in space, where the electron is likely to be found if you look. That's all it is. A probability map. The simplest orbital, the ground state of hydrogen, is a sphere. The probability is highest right at the nucleus and falls off gradually as you move outward. There is no ring, no path, no track, just a fuzzy cloud of likelihood. Higher energy orbitals have stranger shapes. Some look like dumbbells, some look like donuts, some have multiple lobes pointing in different directions. These are not physical objects you could touch. They are probability distributions. Mathematical landscapes describing where the electron might show up if you decided to look for it. And here's something that should genuinely disturb you. The electron doesn't smoothly transition between these orbitals. It doesn't slide from one to another. It doesn't travel through the space between them. It jumps, instantaneously. One moment, the wave function has one shape. The next moment, it has a completely different shape. No gradual change, no in-between state, no path connecting the two. This is what we call a quantum leap. And nobody knows how it happens. The math describes it perfectly. The experiments confirm it every time. But there is no mechanism, no explanation for how the electron gets from one orbital to another without passing through the space in between. It just does. Now let's talk about what the electron actually is. Because this is where things get genuinely unsettling. You think of it as a tiny ball, a little sphere, very small, sure, but still an object, a thing, a particle, with a definite size and shape, just incredibly small. Except when we do experiments, we discover the electron also behaves like a wave. It can interfere with itself. It can diffract around obstacles. It can spread out, pass through two openings simultaneously, and recombine on the other side. All behaviors that only waves exhibit. So which is it? Particle or wave? Neither. The electron is not a particle. It is not a wave. It is something else entirely. Something that has no equivalent in our everyday experience. A quantum object. It exhibits particle-like behavior in some experiments and wave-like behavior in others. But it is fundamentally neither one. It's a new category of thing. One that our brains evolved to understand rocks and rivers and thrown objects cannot properly visualize. When you're not measuring it, the electron is described by a wave function that evolves smoothly over time. It spreads, it interferes with itself. It does everything waves do. But the moment you measure it, the moment you actually detect it, you always find a single localized point. A dot on a detector screen. A click in a measuring device. Never a smeared-out cloud. The spread-out wave function instantly collapses into a single definite outcome. And nobody knows how that happens. Nobody knows what exactly counts as a measurement. Nobody knows where the wave function goes when it collapses, or why it collapses at all. This is called the measurement problem. It has been bothering physicists for nearly a century. There are interpretations, many worlds, pilot wave theory, objective collapse models. But they are interpretations. The math works. The predictions match reality with extraordinary precision. But the underlying picture, what is actually happening, remains genuinely unclear. Now let's make it more complicated. Add more electrons. Helium has 2, lithium has 3, carbon has 6, iron has 26. Each of these electrons exists as a wave function around the nucleus. But here's the thing that changes everything. These electrons are identical, not similar, not alike. Identical. Fundamentally, perfectly, indistinguishably the same. There is no way to tell electron number 1 from electron number 2. Not because they look alike, because they are the same thing, appearing in multiple places. And this identity has consequences. Real, physical, structural consequences. If you swap 2 electrons, the wave function of the entire system changes sign. It picks up a negative factor. This is not a minor technical detail. This is the Pauli exclusion principle. And it is the reason matter is solid, the reason you don't fall through the floor, the reason atoms have internal structure, the reason chemistry works, the reason life is possible, The Pauli exclusion principle says no two electrons can occupy the same quantum state. If one electron is in a particular orbital with a particular spin, no other electron can be in that exact configuration. They have to stack, they have to fill different orbitals, different energy levels, building outward layer by layer. And that stacking is what gives us the periodic table. That stacking is what gives different elements their different chemical properties. Without this rule, all electrons would collapse into the lowest energy state. Every atom would be chemically identical. There would be no complexity, no molecules, no chemistry, no biology, no you. But why does swapping identical particles change the sign of the wave function? We don't know. We discovered the rule. The math works. The experiments agree. But there is no deeper explanation for why this is the case. It simply is. Now, the nucleus. You probably think that part is simple. A bunch of protons and neutrons clumped together. Little balls stuck to each other by the strong nuclear force. Solid, dense, straightforward. It isn't. It isn't. Protons and neutrons are not fundamental particles. They are made of smaller things called quarks. 3 quarks per proton, 3 quarks per neutron, up quarks, down quarks, held together by a force called the strong nuclear force, carried by particles called gluons. But the quarks don't sit still inside the proton like marbles in a bag. They are quantum fields, constantly fluctuating, constantly interacting, constantly exchanging gluons with each other. The proton is not a container holding 3 quarks. The proton is a bound state of the quark field, a stable pattern of oscillation in quantum fields. And here's the part that should genuinely stop you. Most of the mass of the proton doesn't come from the quarks themselves. Quarks are nearly massless. Most of the proton's mass comes from the energy of the gluon field holding the quarks together. Energy has mass. That's what Einstein's equation tells us. Mass and energy are the same thing in different forms. So when you ask what's inside a proton, the answer isn't stuff, it's energy. Bound field energy, arranged in a stable pattern. So let's step back, let's ask the question properly. What is actually inside an atom? Not particles, not little balls, not orbits, not stuff in the way you think of stuff. What's inside an atom is fields. Quantum fields. The electron field. The quark field. The gluon field. The electromagnetic field. These fields fill all of space. They are everywhere. Always. When we say there is an electron in an atom, what we actually mean is that the electron field has an excitation, a localized disturbance near the nucleus. That excitation is what we call an electron. When the quark field has certain excitations bound together by the gluon field, we call that a proton. The atom is not a thing. It is a pattern, a stable configuration of field excitations, held together by forces that are themselves carried by other field excitations. There are no solid objects at the bottom. There is no stuff. There are only fields, mathematical objects that assign values to every point in space and time, values that evolve according to equations, values that sometimes produce localized excitations we call particles. You don't like this. You want something solid at the bottom, something you can point to, something real in the way a rock is real or a table is real. But there isn't. There's math, equations, symmetries, conservation laws. And somehow from that abstract mathematical structure, the appearance of solid matter emerges. Tables, chairs, mountains, your body. All of it is patterns in quantum fields, held together by forces, stabilized by exclusion principles, flickering and churning at scales you cannot perceive. Now here's something else that's going to bother you. You've probably heard that atoms are mostly empty space. The nucleus is tiny compared to the whole atom. If you scaled the nucleus up to the size of a marble, the atom would be the size of a football stadium. Vast emptiness between a tiny center and the electron somewhere out there. But that picture is wrong too. Because empty space doesn't mean nothing. The quantum fields are still there. The vacuum, the supposedly empty space between the nucleus and the electron, is seething with activity. Virtual particles are constantly flickering in and out of existence. The electromagnetic field is present everywhere, and the electron's wave function fills the entire volume of the atom. The electron is there in the sense that its probability amplitude is tangoo throughout. There is no truly empty region inside an atom. And when you push on a table, you are not feeling solid matter resisting your hand. You are feeling electromagnetic repulsion between electron clouds. Field configurations pushing against field configurations. The Pauli exclusion principle, preventing electrons in your hand from occupying the same states as electrons in the table. It feels solid. The forces are strong enough to resist your push, but there is no contact, no touching, no collision of hard surfaces. just fields interacting across distances too small to perceive. You have never touched anything in your life. Not really. Every time you think you're touching something, you're feeling electromagnetic forces pushing back at you through empty space. Now let's talk about size. The electron, as far as every experiment has ever determined, has no size, zero. It is a point particle, a mathematical point with no spatial extent, and yet that point particle somehow participates in a wave function that spreads across a region 10 to the minus 10 meters across. A point with no size, behaving as though it occupies a volume. Does that make sense? No. But that is what the experiments tell us. Nature does not care whether it makes sense to you. Electrons also have a property called spin. It behaves mathematically like angular momentum, like the electron is rotating. But the electron cannot be spinning. It has no size. A point cannot rotate. There is nothing there to spin. And yet spin is real. It is measurable. It affects how atoms behave, how chemistry works, how matter is structured. Spin is intrinsic angular momentum that does not come from physical rotation. We call it spin because the mathematics resembles angular momentum, but it is not rotation. It is something else entirely. Something with no classical equivalent. Spin is also quantized. You can measure it along any axis, and you will always get one of exactly two answers, up or down. Never anything in between. Never a partial value. Before you measure it, the spin doesn't have a definite direction. It exists in superposition, and the moment you measure along one axis, it becomes uncertain along every perpendicular axis. Why? Nobody knows. That is simply how spin works. Nothing in your daily experience behaves this way. Nothing. Energy levels in atoms are quantized too. The electron can only have certain specific energies. Not any value. Not a smooth continuum. Specific, discrete, allowed values. Why? Because the wave function has to fit around the nucleus. Think of a vibrating string. A guitar string can only vibrate at certain frequencies. The fundamental tone and its harmonics, random frequencies don't sustain themselves on a string with fixed endpoints. The wave function works the same way. Only certain wavelengths fit. And since energy is tied to wavelength, only certain energies are possible. When the electron jumps from one energy level to another, it emits or absorbs a single photon, carrying exactly the energy difference between those levels. This is why atoms emit light at specific wavelengths. Hydrogen has its characteristic spectral lines. Each line corresponds to a specific transition between energy levels. We can measure these wavelengths with extraordinary precision. We can predict them using quantum mechanics with extraordinary precision. They match to 12, 14 decimal places. The theory works with astonishing accuracy. But why are energy levels quantized in the first place? The math tells us they are. The experiments confirm it. There is no deeper reason behind the reason. It is a structural fact about how wave functions behave in the geometry of atomic systems. And here's the final thing that should unsettle you completely. You cannot observe what's inside an atom without changing it. You can't use visible light, because visible light has wavelengths larger than an atom. You need higher energy probes, shorter wavelengths. But the moment you use those probes, the moment you direct high energy particles or radiation at an electron, you disturb it. You knock it out of whatever state it was in. You alter exactly what you were trying to measure. This is not a technical problem. It is not an engineering limitation we might solve with better instruments. It is a fundamental constraint built into the structure of reality itself. To observe something at quantum scales, you must interact with it, and interaction changes it. There is no such thing as a passive observation at this level. There is no way to look without touching. The act of measurement does not reveal a pre-existing state. It creates one. So what is really inside an atom? Not little balls, not orbits, not stuff, not particles in the way you think of particles. What is inside an atom is a mathematical structure, a wave function, a solution to the Schrödinger equation, a pattern of probability amplitudes that tells you what you will find if you look, but does not describe a definite reality when you are not looking. The atom is a quantum system, and quantum systems do not behave like anything in your everyday experience. They exist in superpositions. They have properties that are fundamentally uncertain until measured. They defy visualization. You cannot picture what's inside an atom because there is nothing to picture in the way your brain expects. The wave function is not a physical wave rippling through space. It is a function defined in an abstract mathematical space called Hilbert space. It is a collection of complex numbers encoding probabilities. It is information, not substance. And yet from this abstract structure, the entire physical world emerges. Chemistry, biology, consciousness, all of it built from patterns in quantum fields, governed by equations, following rules that make no intuitive sense whatsoever, but work with a precision that is genuinely breathtaking. This is what's really inside an atom. Not particles, not matter, not stuff. Math, abstract, precise, beautiful, deeply uncomfortable math. And if that doesn't satisfy you, if you still want something solid and real at the bottom of it all, something you can hold in your hand and say, there, that's what everything is made of. I'm sorry, but the universe doesn't care what you want. It is what it is. And what it is far stranger than anything you were ever taught.